welcome once again to RF transceiver design course. We are discussing about active devices, and in last class we have broadly classified the various types of materials that are used to make the RF devices, and we have also defined the difference between IPT, HPTs and even HAMT. The basic has been cleared, it is covered in the last class. We will discuss that one more point that I want to add, that is a power amplifier performance in HPTs and mostly in HAMTs. So, because power amplifier is a big market, and this is only considered based on the reference, it is 2 gigahertz, but this will classify based on the technology what are the performance that is achieved. So, the mostly here you if you see the power gain means in indium or gallium arsenide base HPTs, it is gain is 31 dB, maximum output power you will get is 27 and efficiency is 35 percent. And this is a company which are dominating and working on making this kind of devices and power amplifiers. Then there is a indium phosphide gallium arsenide HPTs, which again has a similar performance ACPR at 5 megahertz DBC. So, DBC we already have discussed in the when I discussed the unity, that is minus 37 dB, and the efficiency is 38%. Indium phosphide gallium arsenide HPT, again if these are the various group RFMD, MACOM, NEC, these are manufactured of these devices, and they have demonstrated the efficiency up to 50.5%. Gas HFET, high frequency FET, by using gas, NEC has also achieved the efficiency of 47.2%. Even PHAMT Motorola has used, and they achieved efficiency up to 25.6%. However, the dominating and the best performance is you will get is a GaN HAMT, and that is a 54%, and Cree, which is made by the group Cree. So, GaN is dominating in terms of the power amplifier performance, and it is widely used. However, you can also use other technology for designing a power amplifier. So, if you are more interested to understand the devices, you can go for each devices based on the literature that is available. So, now we will try to go for the design part, means what are the basic understanding that you required about the active devices when you start designing the RF components. So, if we make any device as a generic 3 terminal device, so here it is a generic model is given. So, generally what we will do, that our output current, so this is a 3 terminal device, this output current and this is the input voltage. So, your output current is a function of input voltage and output voltage in any, this can be applicable to any active devices or 3 terminal components, where your output current is a function of input voltage and output voltage, and mostly it is a function of input voltage. So, there are 4 types of devices that can be given as example here, that is NPN BJT, N channel JFET, NMOS and gallium arsenide based MOSFET. So, these are the symbols to show on in the circuit for each devices. Now, for any generic devices, if we have a certain type of IV characteristics, means output and output voltage characteristics, which is a function of output current voltage characteristics, which is a function of input voltage, that can be given by this diagram. So, how exactly the means this is very important as far as active component is concerned, because if you are a device engineer and if you make a device which does not have these characteristics that you achieved, then it can be not used as a it cannot be used as a amplifier. So, here your output current is a function of and output voltage with various variation in the input voltage. So, this can be if we start from the if you start from the vacuum tube to the bipolar or any devices, this characteristics is a true. We can apply these characteristics and you will get these characteristics from all these devices. So, mostly it is a it can be divided in 3 region. We all know that if your current and voltage, if this is a linear function, then if your voltage and current is a linear function, then that is a mostly resistive behavior. So, in this much region, because it is a linear function of the voltage your current, that is why it is a mostly resistive. Now, the moment it will be it will transit from the nonlinear to the saturation. So, what how do you model this constant current? It is a straight line. So, this is a voltage and current. So, the constant current is modeled as a straight line. So, here the at moment when there is a constant current, that means it is a in small signal you can consider it is a constant current, and the region in between these two, resistive region and that is called saturation region, if it is a FET, or it can also be mentioned as active region or constant current region, and the in between these two is a non-linear region. So, these can be applied to any characteristics, means any devices which has a output characteristics, output voltage characteristics looks like this. So, bipolar, for bipolar output current is written in the exponential function. For FET and MOSFET, which is work in pinch off regime, the ID current is equation is written in this form. Then here this is a square function of input voltage, and similarly MOSFET is also square function, and vacuum tube which is not longer in use, but for the analogy purpose it is kept here, that any device this generic model can be applied. And why it is called a large signal equation, because we are going to sweep the voltage from 0 to the maximum voltage with the variation in the input voltage. So, which will give us the complete profile of the device. So, mostly it has a 3 region, one is a resistive region, then there is a non-linear region, small output voltage, then saturation or a constant current region. So, this can be applied to any devices that we use in our RF application or any application where amplification is involved. So, let us discuss the MOSFET. So, in this PPT what we have divided, that MOSFET and BJT, which are the widely used components, and the detailed study about this basic MOSFET and BJT is discussed. So, MOSFET is a 4 terminal device, as we all know. It is a there is a P plus if it is a P, this is a N substrate, and EP this is a called this is NMOS, which is a N channels, and this is a PMOS, which is a P channel. So, here the channel will be made by holes and here channel is made by electrons, and this mostly NMOS and PMOS, only the interchange in the drain and source you can use the same equation. So, ID current equation of the MOSFET and MOSFET is given by because it is right now considered for N MOSFET, it is a mu n C ox W by L, where W is the width of this MOSFET and L is a length. So, this L effective is because there is a on the overlap on drain, gate is a overlap over the drain. So, this is a LD. So, generally L effective is written by L minus 2 LD, because on the drain side also there is a overlap and on the source side also there is overlap. So, that is why L effective is mentioned as a L minus 2 LD. So, this is a equation of ID, which is a mu n C ox W by L VGS minus VTH VDS minus 1 of VDS square. If we discuss about the ID current, and here mu I just want to mention mu is a mobility and this is a oxide capacitance, and VGS is a gate to source voltage and VTH is a threshold voltage, VDS is a drain to source voltage, and this when we try to find out the ID current equation, there is a channel. So, as you apply the gate voltage here and there is a sufficient drain voltage is applied, there is a channel will be formed, which is the from P substrate electron will come at the gate side and that will form the channel, and due to this channel there is a current will flow from a source to drain. So, this is how the current and based on this phenomena that current equation is come. If you are interested more in detail that how this came, you can go back and just revise your semiconductor physics. So, if you try to draw the same equation with various VGS 1 to VGS 3, means increasing the VGS voltage and ID versus VDS plot, because this is a ID and VDS has a relation with variation of the VGS, it is a parabolic plot. And we can see from this that at different if it is at different stage, the maximum current is given when your VGS 1 let us say VGS is minus VTH. So, if your VDS if your VDS is greater than or equal to VGS minus VTH, then you will have a maximum current. So, in the same equation, this ID equation, if we write VGS VDS which is equal to VGS minus VTH, we will get a maximum current ID max, that is given by ID max, which is half mu n C ox W by L VGS minus VTH square. This can also be in some books, it is also be mentioned as a K. KWL, half mu n C ox is defined as a K some constant K, Kn or Kp for PMOS. Now, this is a region where when your circuit is in saturation. Now, here this when there is a triode, means less than this, when your VDS is less than this 2 VGS minus VTH, it is in a triode region, because it is a linear function of voltage, your current is linear function of voltage, then we can write VGS which is in the ID equation VGS minus VTH into VDS, where VDS is too small, we have neglected the, in this equation we have neglected this term because VDS is too small, and then considered only this VGS minus VTH into VDS. So, your current is given by mu n C ox W by L VGS minus VTH into VDS. Your on resistance means that is given by 1 by mu n Cox W by L VGS minus VTH. So, you can have a this is a let us say drain and source, and then you can consider it as a resistance, which resistance is a variable with the gate voltage. So, this can be also used as a variable resistor, which resistance will vary, because all other all other terms are constant, only VGS is that is varying. So, we can by changing the gate voltage, you can change the resistance of the same. Here the threshold current equation is given by 5 ms, where 5 ms is a work function, it is a work function difference between metal and semiconductor, because at the gate you have a metal and semiconductor junction, and that will add a difference, that is a 5 ms work function difference 5 ms. So, your VTH is depend upon that 5 ms value. Then this is a Fermi potential phi f, which is given by kT by q ln of n substrate minus Ni. So, this is a substrate doping density, and this is a intrinsic material density. So, that will give you the F5 F, and there is a Q depletion, which is a charge. Q depletion is a charge in the depletion region. So, this Q depletion has also equation, I will note it down somewhere here, which is a square root of 4q epsilon 4q epsilon, this is a silicon epsilon, then 5f into an substrate. So, based on this all parameters, your threshold voltage is defined, and this is a constant for any process that you are using. And oxide capacitance is given by epsilon ox by T ox. It is in the range of 3.45 femtofarad per micrometer square, where oxide thickness in the range of angstrom, 100 angstrom, and based on the device technology, this might vary. So, what are the three basic region that you should know? That is a cutoff, saturation, and triode region. So, if your NMOS transistor, if we consider NMOS transistor, for cutoff region your VGS is less than VTH and your VGD, gate to drain voltage, is a less than VTH. For saturation, VGS is greater than VTH and your VGD, which is a less than VTH. You can also mention your VDS should be greater than or equal to VGS minus VT, and VGS is greater than VTH. This can also be written. Then triode region, it is a VGS which is a greater than VTH. We already have defined the triode region, your VDS is less than VGS minus VTH. So, there is a channel needs to be formed, but it is a linear in this region, that is why your VDS is a less than and it is not giving the constant current, only the linear function of voltage. So, your VGD which is a greater than VTH. So, this is the basic large signal analysis. So, we can define the any active component in the two characteristics, where one is a large signal, where we try to find the operating point and where our device we would like to make it work. And mostly in amplifier, if we try to use it as amplifier, it is a bias in the saturation region. So, this will give us the complete idea that in what region you should bias your transistor. Once it is biased, then it will act as a linear devices, and it will have a very small signal that is applied, which will be amplified. So, that is another case where which is a small signal characteristics. So, uh, for any devices, if you want to understand the characteristics, it is always important to do analysis of large signal and a small signal. So, now we will try to move for the small signal analysis. So, if you have bias your transistor in a saturation region, in MOSFET in saturation region, then this is um, a model, small signal model that will look like. However, this is considered a capacitor. So, if you are not considering the capacitor, the mostly this is a widely used model. So, this is a drain, this is a gate, this is a source, you have a VGS voltage plus or minus, then this is a GM into VGS. So, this is a small signal model for low frequency application, and many amplifier, while discussing the amplifier we use this MOSFET small signal model. The input is a open circuit, there is current is not going to flow in the gate, only there is a output current which is depend upon the input voltage VGS. So, if as we have discussed in the last class, transconductance is important, which define the amplifier performance. So, that is a del ID by, so GM, which is equal to del ID by del VGS. So, various equation can be find out. So, ID current, if we write del by del VGS, then half mu n C ox W by L VGS minus VTH whole square. So, if you derive it with a VGS, you will get a mu n C ox W by L VGS minus VTH. So, this is one of the equation of GM. Now, if you try to include the current, if you try to use the current equation together with this equation, you will get a square root 2 ID mu n C x W by L. So, in this case your GM is a linear function of VGS. However, if in this case your GM or GM by ID is a function of 2 by VGS minus VTH. So, if you just divide GM by ID, this is the equation. So, this different equation has a different meaning. Let us say here if you are considering the current constant. So, when you are using this equation, your current is a constant. So, and when you are using this equation, your gate means gate to source voltage is a constant and you are varying the current ID, and in this case your it is depend upon the you are changing the W and W by L. So, this is how you can define the transconductance for various which you are considering as a constant, and it will vary, but you will get the difference. The transconductance will remain same, that is a GM, and based on the what kind of current, what kind of variable that you are adding, it will change. Either you are varying the width, you are varying the gate to source voltage, or you are varying the current which is flowing through the transistor. Now, because MOSFET is a 4 terminal device, we cannot avoid the body effect, and that is the body effect transconductance, and because because body is a 4th terminal and it can be act also as a one of the gate. Now, that will give the another GMB, that is a function of source to bulk voltage. So, based on the source to bulk voltage, it will. So, here this is a N plus, this is a gate, and then you have a, this is a P substrate and this is a body P plus. So, while applying to voltage to the generally this both will be connected to ground, but when we try to connect some resistance, or if there is a change in the potential in the source, let us say if this is a common source amplifier with a source T generated load, then this potential not be the ground, and because of that we need to consider the change in the potential between base to source. So, that will also add the GMB in, that is why GMB is coming into the picture, and in this model here we should also consider GMB into VBS, that is a body to source voltage, and then there is a RO. So, that is why here GM VGS and GMB VBS both is mentioned. So, this is about the body effect transconductance GMB, and it is a function of 5F that we have seen in, and this is a process dependent parameter gamma, and this is a GM. Even there is a channel length modulation that is occurring in the MOSFET, and that channel length modulation happens because that also if this is a N plus and N plus and this is a gate, as your drain voltage is high and you are increasing the threshold voltage, the point at which there is a pinch off will occur, and there are more electrons on the source side compared to the drain side, and there is a small barrier will be there, that will, because of the high electric field, the electron will move from this source to drain. So, this channel will be formed. Now, because of this pinch off, and there is a channel length which is modulated based on the drain bias, that by changing the drain bias, what will happen that in your output characteristics we generally have a constant current that we want, but in reality it is not constant, it is a varying with the drain voltage, and that is that variation is because of this channel length modulation. And that channel length modulation, if you try to plot this at the back side, there is a, if you asymptotically take it on the other side, you will get a voltage that is called a early voltage VA, and that lambda is depend upon the early voltage VA, and it is given by 1 by L effective. So, it is inversely proportional to the length into del xt by del VDS. So, this is a channel length modulation you should consider, and these are the known ideality of MOSFET. In ideal MOSFET, this parameters will not be there, but when you, because we are working at RF, and at RF frequency you also need to consider the non idealities. You are working at very high frequency, and when we are working at very high frequency we also need to consider the capacitance associated with the each device terminal. So, if we try to draw MOSFET, then and if we consider the bulk, it is a CGD capacitor between gate to drain, then it is a CDB capacitor between drain to bulk, again source to bulk there is a capacitor, gate to source there is a capacitor, and the gate to bulk there is a capacitor. So, how this if we draw the cross section, we can get a idea of, this is N plus, this is a gate silicon oxide and the gate, this is SiO2, that is the insulator, this is a gate, this is a drain, and this is a source. So, because there is a channel will be formed. So, between channel to bulk there is one capacitor that is called C channel to bulk CCB. There is a capacitor between, because N plus and P there is a junction, and that N plus P junction will have a junction capacitance. So, this has a C junction source to bulk, this is a capacitor which is a C junction. So, this is a bulk P substrate, and this is a source junction, source to bulk and drain to bulk. These are the capacitor, and we will try we will see all other capacitor also based on this 3 capacitor. So, you can get your junction capacitance CGC, which is a function of C ox W L effective, because there is a oxide capacitance C ox, and that will be multiplied with the width, because your area is W into L effective. So, this is a total junction capacitance GC. Your oxide capacitance C ox, as shown in the last class, it is a epsilon ox by thickness of oxide, and your overlap capacitor C overlap, because there is a overlap of drain over the source, overlap of gate over the drain, and overlap of gate over the source is there. So, because of that there is a overlap capacitor, and that is given by WLD, because this is a overlap length, that is LD into C ox. So, this is a overlap capacitor, that is that will be there in the MOSFET. Now, based on the based on where, in which region your MOSFET is, we can make the graph of let us say for when your triode, when your MOSFET is off or on, or it is in triode region, your capacitance will change. So, we are stopping here. We will discuss about this capacitor more in detail in the next class. Thank you.